Alright, the sole purpose of this video is to make an intuitive argument for the centripetal acceleration. Assuming that you have some object that's moving in a circle at a constant speed, it has a certain velocity that's always tangent to the circle. Here it is at one time t, and here it is at a time t later, so that the velocity vector initially in this direction is over in this direction after a certain amount of time has elapsed, or you've swept through a certain angle. If you take this final vector and place it at the tail here of the initial vector, you can see that the change in velocity, delta v, is just equal to this little vector right here, which points approximately radially inward. As you have a smaller and smaller angle, then this is more and more toward the center of the circle. Maybe you can see that from this picture. This particular change in the radius is from the initial position to the final position. So there's a vector delta r that represents the change in position from the initial position to the final position. If you look at these two triangles right here, they are similar. And also using Mr. Todd's rule, if you look at this side of this angle, this side right here is perpendicular to this side, and this side is perpendicular to that side. That makes this angle right here also theta. And since these are similar triangles, I can say that delta v, just the magnitude, delta v over v is equal to delta r over r. I know my r's and v's look similar, but this is a little r here. And if I divide both sides of this equation right here by delta t, 1 over delta t here and 1 over delta t here, then on this side I have delta v over delta t, 1 over v is equal to, I have delta r over delta t, 1 over r, like that. And this is just the magnitude of the centripetal acceleration, and this is just the magnitude of the velocity. So I have that a times 1 over v is equal to v times 1 over r, or multiplying both sides by v, I have a is equal to v squared over r. So this is just an intuitive semi-quantitative argument to show that the centripetal acceleration, the magnitude of it, is v squared over r for uniform circular motion. And you can also see somewhat intuitively that the change in velocity is always toward the center of the circle, so that the centripetal acceleration, a as a vector, is equal to v squared over r in the radially inward direction, or the minus r hat direction.